We're going to look at a few situations similar to some of the items that occurred on the test. If we have a 10 kilogram mass that descends 20 centimeters, as it rotates an object whose moment of inertia is 0.03 kilogram meters squared, and rotates that object from rest, then the question is, what should the angular velocity of the object be? If we make our first order assumption that all the potential energy change of the descending object goes into the rotational kinetic energy of the other object, then our change in kinetic energy is going to be just 1/2 I omega squared, where omega is the angular velocity we attain. Remember that the change will just be equal to the kinetic energy since we're starting from rest, where the kinetic energy was 0. And that's going to equal the negative of the change in potential energy. Again, change in kinetic is negative the change in potential when there are no external forces or no dissipative forces acting on the system. Proceeding symbolically here, we set 1/2 I omega squared equals negative delta PE. What's a change in potential? Well, let's just solve for omega. Okay, omega is going to be easily solved. We're going to get this expression. Multiply 3 by 2, divide by I, take the square root. Our delta PE is going to be negative 20 centimeters times 10 grams times 9.8 meters per second squared. Okay, 10 grams is the mass. Multiply that by the 9.8 meters per second squared. We get the weight, which is the force of gravity, times the negative 20 centimeters. And we have the change in potential energy. Now we're going to have to convert this to 0.02 meters and this to 0.01 kilograms, but by the time we've done that, we're going to end up, let's say 0.02 meters, 0.2 meters, and 0.01 kilograms. In any case, we're going to end up with negative 0.02 joules of potential energy change. Having obtained that, it's going to be very easy to obtain our omega. And the omega is just going to be what we get when we take the square root of all this quantity and work out the units to be sure that we're doing it right.